In example 2, we've been asked to find the local minimum and local maximum points for this third degree polynomial. So first, we need to find the derivative function. So we drop down the 3. 1/3 times 3 is 1. So 1x to the second minus, drop down the 2, we get 6x, and the derivative of 9x is 9. And of course, you don't need to write the 1 out front. The leading coefficient is 1, but we could just write x squared minus 6x plus 9. Second step, we need to use the derivative to identify all critical points of the function f of x. That is, all points where f prime is undefined and all points where f prime is 0. I first observe that f prime of x is never undefined. F prime of x is this second degree polynomial. It's a quadratic function. You can plug in any x value and you will get a real valued y out of it. So there are no critical points where the derivative is undefined. But we can find points where the derivative equals 0. I set the derivative equal to 0. One way to solve this would be to factor. This factors as x minus 3 times x minus 3. And so we find that the solution to the equation is only one value, x equals 3. One solution to where the derivative is equal to 0. Another way to solve, if you don't like factoring, is to use the quadratic formula. So that's x equals negative b plus or minus square root of b squared minus 4ac all over 2a. So you'll get negative 6, so 6, plus or minus negative 6 squared, so 36, minus 4 times a times c, so 4 times 1 times 9, all over 2 times a, so 2 times 1. That is 6 plus or minus the square root of 0 over 2. So you'll get x equals 6 plus 0 over 2, and x equals 6 minus 0 over 2. So both answers come out to just 3. There's still only one solution, one x value that solves the equation, x equals 3. I'm now going to write my interpretations, my conclusions that I draw from this solving. I can now say f of x has exactly one critical point at x equals 3. That's one place where the derivative of f is equal to 0. In other words, it's one place on the graph of f where f is flat for an instant. Note this is the only place where f of x is flat for an instant. Everywhere else on the graph of f it must be increasing or decreasing. This is the only place where it flattens for an instant. So step 3, we need to test using the first derivative, because this is the first derivative test. We are testing to see if our critical points are local maximum, local minimum, or neither. In order to test, I draw a real number line to indicate the entire domain of f of x. The domain of f of x is all real numbers. I then put my critical point, there's only one, right on that number line. I'm going to make my conclusions about what's happening right at x equals 3. At x equals 3, the derivative is 0. At x equals 3, f is flat for an instant. Now I pick an x value to the left of x equals 3 and an x value to the right of x equals 3, and I evaluate f prime. I'm going to try f prime of 0, so I'm picking x equals 0 on the left side. If you evaluate the derivative function when x equals 0, you plug it into the derivative function, you will get f prime equals 9. I know then that over here on the left side of x equals 3, f prime is positive. The derivative is positive, so I know f is increasing. Then on the right side, I'm going to pick x equals 4, and I'm going to evaluate the derivative at x equals 4. You will get out a value of 1, so that tells me over here on the right side of x equals 3, f prime is positive, which tells me on the right side of x equals 3, f is increasing. So based on this, I can now conclude that the function f must look like this. It's increasing, then flat at x equals 3, and then it keeps on increasing. So f of x must look like this. X equals 3 is a critical point, but it is not a max, and it is not a min. It's just a point where f of x flattens for an instant, but it's not a local maximum or a local minimum. I could then come on over to Excel and verify everything that we just learned here. So in Excel, I've put in the function in column B, and I've put the derivative in column C. You'll see here at x equals 3, we see a derivative value of 0. And so at x equals 3, we know f of x is flat for an instant. We see on the interval from negative infinity up to x equals 3 that the derivative values are positive. Therefore, on the interval from negative infinity up to 3, the f of x function must be increasing. And finally, we see on the interval from 3 up to positive infinity, again, the derivative values are positive. Therefore, on the interval from 3 to infinity, f of x is increasing. Now we know f is increasing, then flat, and then still increasing. Therefore, we can conclude x equals 3 is not a local max and not a local min. And since this was the only critical point, we can conclude that f of x has no local max and no local min.